Nuclear magnetic resonance spectroscopy, also known as NMR. Okay, so when NMR is coupled particularly with infrared, mass spec and elemental analysis, it's a very powerful analytical tool in order to determine the structure of a compound. And the aim of this short video is to go through the key points for A-level chemistry, particularly OCR A-level chemistry. What do you need to know about NMR and how do you interpret the spectrum? So first, when an organic molecule is placed in a strong magnetic field and subjected to low energy radio waves, then analysis of the energy that's absorbed is the nuclei that absorb this energy, and this leads to an NMR spectrum. And you're expected to interpret the spectrum. Now there's two types of NMR for A-level chemistry. There's 13 carbon NMR and proton NMR, hydrogen NMR. Proton NMR. Now interestingly, NMR is only on odd mass number. It only works for odd mass number. So if it's an even mass number, like in deuterium, the isotope of hydrogen, then that doesn't show up, is not detected on NMR. Now for both of these NMR techniques, you need to add to your organic molecule, you need to add some TMS. TMS stands for tetramethyl silane. Tetramethyl silane. Okay, now the purpose of this is to calibrate the spectrometer, to tell the spectrometer, the machine, where zero is. Yeah, to calibrate the spectrometer, spell it carefully there, yeah, to tell the machine where zero is. The formula tetramethyl is 4 methyl groups and a silicon, and that gives the zero peak on the NMR. Something else that you need to add to your NMR sample is a solvent, and the solvent is CdCl3, and the D stands for deuterium. Deuterium is one of the isotopes of hydrogen, and because it has an even mass number, it is not detected in the NMR, NMR spectrum. Okay, so those two chemicals need to be added to your sample. So when you're looking at the data sheet, you have to be able to interpret the spectrum. We're going to start with carbon NMR first, and I'm using the OCR A-level chemistry A data sheet. Yeah, and we're going to look at the carbon NMR. Now, you're never given just an NMR in isolation. You're always given some other information as well. So we're going to look at the NMR of the molecule, and the molecular formula is C3. The molecular formula is C3H6O. Okay, now things to look at first. The axis at the bottom is a bit unusual because it's going in the reverse direction. Here's the zero, here's the TMS that has given us the zero peak on the spectrum. Okay, and this here, this delta, this stands for the chemical shift. Yeah, and the chemical shift just means the shift in frequency compared to TMS. So compared to TMS, the shift depends on the chemical environment. Yeah, it depends on the environment of the carbon atoms. And in bold, we have the carbon atoms because we're just looking at, this is carbon NMR. Okay, now quite often when students are given carbon NMR spectrum, they spend a lot of time analyzing it. But actually, you should start with the formula. You've been given a molecular formula. There are only 3 carbons, and your job is to identify what the molecule is that's made the spectrum. So there's only 3 carbons, so you really haven't got many options, potential options. Okay, there aren't many hydrogens, so therefore you're either looking at a ketone or you're looking at an aldehyde. Okay, I haven't drawn on all the hydrogens because I haven't got much room here on the slide to draw the hydrogens. Okay, so let's start with the aldehyde. Let's start with propanal. Okay, how many different carbons are there? How many carbon environments? Okay, now is it possible to see that this very first carbon here is a C double bond O? There isn't another C double bond in the molecule, so that is one carbon environment. The very next carbon is a CH2. There isn't another CH2 in the molecule, that's another carbon environment. And the last one is the CH3, sorry, just rub it back in, the CH3, and there isn't another CH3 in the molecule. So propanal has 3 carbon environments, 3 types of carbon in its molecule. Whereas when you look at propanone, you do have some symmetry there, yeah? You have a plane of symmetry. And can you see that the CH3 on the left and the CH3 on the right are actually identical to each other? So they are both CH3s and they're joined to the same C double bond O. So that is called one carbon environment. And then you have another carbon, which is your C double bond O. Therefore, propanone has got 2 carbon environments in total, 2 carbon environments. Now, in the carbon NMR spectrum, you have got 3 peaks. Okay, you've got that peak there at just over 200 ppm, parts per million. You've got a peak at just over 30 parts per million, and you have another peak here which looks like it's about 10 parts per million. So you've got 3 carbon environments. Therefore, this spectrum cannot be propanone because propanone has got 2 carbon environments. This spectrum must represent propanal. And then when we look more carefully at it, we can see at just above 200 ppm that is a C double bond O. So this carbon here, carbon 1, has made that peak. It's a C double bond O, so that matches. Okay, we've got 2 more carbon environments, and they both match just a simple CC bond. So these are carbon 2 and carbon 3, and they are the C to C bond. So that spectrum is a spectrum of propanal. So what information does Carbon NMR tell you? It tells you the number of carbon environments. That basically means the number of peaks. It tells you the type of carbon environment, which you can determine from the chemical shift. You look at the data sheet and get the chemical shift off the data sheet. Okay, let's just spend a moment before we move on to Proton NMR thinking about carbon environments. So there's a bit of a skill with this, yeah, being able to identify how many individual carbons there are. So let's take A for example. You need to see, is there a plane of symmetry? Can you fold this molecule? Is it possible to fold this molecule in half? And it is, yeah? And you should be able to see that that carbon, CH3, is identical to that carbon. And what we mean by identical is that both CH3s are joined to a CH, yeah? So, and that CH is joined to a CH2. So it's the environment, what is around the carbon atom. And then we've got a CH, and those two are identical. They are both CHs joined on one side to a CH3, on the other side to a CH2. And you can hopefully see where this is going, where this is leading. Those 2 carbons are the same, and then finally these last 2 carbons are the same as well. So therefore there is 1 carbon environment, 2 carbon environments, 3 carbon environments, 4 carbon environments. 4 carbon environments. So in the carbon NMR, this molecule will have 4 peaks in the carbon NMR, 4 carbon environments. in the carbon NMR. Right, let's have a look at molecule the isomer B. Is there a plane of symmetry? And hopefully you can see this and you're going faster, quicker than me on this. There's a plane of symmetry down there. And we have this carbon is the same as that carbon is the same as that carbon, that one is the same as that carbon. Now we have a CH2 here, which is unique. There isn't another CH2 in the same environment. And when we say environment, go beyond the CH2 and look at what it's joined to. And here we have an individual as well. So we have 1 carbon environment, 2 carbon environments, 3, 4, and 5. That molecule has 5 carbon environments, therefore 5 peaks in the carbon NMR. The last example, the last isomer, is even more trickier, yeah, because there are 2 planes of symmetry. So you could fold it across, and oops, wobbly hand, I'm sorry, and you could fold it going down, yeah. So you've got that carbon is the same as that carbon. That carbon is the same as that carbon. And can you note that each of these carbons are now the same as each other if you look at what they are joined to on either side? So we've got 1 carbon environment, 2 carbon environments, 3 carbon environments. This will have 3 peaks in the carbon NMR. Okay, on to proton NMR. So now make sure you're looking at the other part of the data sheet, and it's the hydrogens are written in bold. Okay, the scale is different as well. It's a very much shorter scale as well, up to 12. So here we have a molecule, and again, you're never given the information in isolation. This is actually a spectrum of ethanol. Okay, so let me just draw up an ethanol, and this is the proton NMR. So we're particularly concerned about the hydrogens. So I'm going to very clearly draw my hydrogens on my molecule. It's not about the carbons anymore, it's about identifying the hydrogens. Now I've sketched this, and that's why the spectrum looks like that, because I've sketched it. Okay, so we're going to go through each part of the information. The number at the top is the area under the peak. Yeah, is the area. And that number at the top tells you the number of identical hydrogens that have made that peak. Okay, it's the area, and it tells you the number of identical hydrogens that have made that peak. So by seeing, it's the area. By seeing the number 3, I know that 3 hydrogens have made that peak. Now the chances are, therefore, it is a CH3. Let's look at our molecule, and we have got 3 identical hydrogens. They're all sat on the same carbon. Those 3 hydrogens have made that peak. Yeah? The next thing we need to look at is the splitting, right? So the hydrogens are affected by the hydrogens around them. Yeah, the hydrogens around them interact and split the signal. So in a carbon NMR, you've always got a single line. Can you note here that we've got 3 lines? Yeah, we call that a triplet. 3 lines. It's split as a triplet. Okay, 1, 2, 3. It follows Pascal's triangle in its shape, and the maths behind it as well. So we say 3 lines, it's split, the signal has been split into 3 lines. Take away 1 equals 2. That information tells us that there's 2 hydrogens on the next adjacent carbon, yeah, on the adjacent carbon. That's what that information tells us. There's 2 hydrogens on the adjacent carbons. Yeah, so we look at the very next carbon, and yes, there are 2 hydrogens on the next carbon in the molecule. So that works, yeah? So CH3 made that peak. The signal has been split because of the hydrogens interacting, and there's 2 hydrogens on the next carbon. Okay, let's look at the next. Also, sorry, just to say as well quickly, you look at the chemical shift, and what does the chemical shift match? We go down, and the chemical shift matches a HCr, and that works as well because it's a H, a C, and an R. Okay, let's look at the next one. So the next one, and like I said, you can race along with this. The 2 at the top means that 2 hydrogens made that peak. Well, that fits because there's 2 hydrogens. That works. The splitting, we call that a quartet. Okay, I'm just going to squeeze the word in here. A quartet is what it's split into 4 lines. So we say 4 lines, it's split into 4 lines, take away 1 equals 3. So that tells us that there are 3 hydrogens on the adjacent carbon. So we look at the molecule and we look, and yeah, there you go. Yeah, on the very next carbon there are 3 hydrogens. So that works as well. Okay, and then we see what type of proton is it. So you come down to your table here, and there's lots of protons there. Right. Well, we know it's not the halogens because there isn't a halogen in there. So it must be HCO. And we look, is that correct? And it is correct, HCO. What type of hydrogen is it? It's a HCO. Well, that fits as well. Okay. Now the last hydrogen, and we look carefully for the last hydrogen, has an area of 1. So that means it's 1 hydrogen. And we've only got 1 hydrogen left, yeah? So that must be the OH. Now the OH and also NH never splits. It is always a singlet, right? And you notice something there a little bit tricky about the OH and NH. Look at the range where the OH and NH can appear like anywhere there. So it does make it quite difficult assigning OH and NH. Okay, so therefore OH and NH are always single peaks. They cover that wide chemical shift range, so really difficult to assign. So what we do is we first run a Proton NMR, then we add D2O to the sample. So you run the Proton NMR, take your sample out and add D2O, heavy water. And what happens is there is an equilibrium that happens. So the OH, and this also happens with NH as well, the OH and the H and the D swap over. So it becomes OD and HOD. But deuterium is not detected in the NMR. So as soon as the OH becomes an OD, you rerun the NMR and then the peak will disappear. And you will know then that that is the OH peak or the NH peak because the peak has disappeared. Okay, so I hope you found that helpful and useful, and I particularly hope that 13C found that useful too. Thank you.